Ever wondered what is happening inside a beam when it is loaded? How does it withstand forces acting on it? That's where shear force diagram comes in. In this video, I will break down shear force diagrams, what they are, how to draw them, and why they are critical for understanding structural behavior. Whether you are designing a bridge or just preparing for engineering examination, mastering shear force diagram is absolutely must. This is part of my video series on IStructE certificate in structural behavior, or simply if you want to improve your basics of structural engineering, this video is for you. By the way, if you're new here, I'm Dr. Jawed Qureshi, a senior lecturer in structural engineering and design. Here, I will teach you basics of structural engineering. In this video, I will be solving 4 examples. So pay attention and grab your pen. Let's get started with the first example. In this lecture, I will cover shear force diagrams for simple and complex beams. In this example, we have to identify the correct shear force diagram and ignore the self-weight. It's very important to note that anti-clockwise forces are positive. Sign convention for anti-clockwise forces is like this. When we have upward force from right side, it is considered as positive, and downward force from left side is considered as positive. And in this way, it is creating anti-clockwise moment. So this is the sign convention which I will be following for this problem. And if the clockwise forces are positive, then the direction of arrows will be reversed. But the question is that how do we draw a shear force diagram? This is the sign convention for shear force diagram. Positive forces or upward forces from right side are drawn on the positive side of the beam. This is 0 axis, and the negative forces are drawn on the downward side of the beam. So remember these 2 sign conventions when we solve this problem. There are 4 options to choose from, and I will use process of elimination to eliminate certain options. Having a look at option D, at free side, I don't have any loading at all, which means that this is not possible to have a loading at free end. We have a uniformly distributed load which will not generate any loading at the end. It means option D is incorrect. How about option B? Same is the case with option B. If I'm starting from right side, you can see we have load over here at the free end, which is not possible. It means I will discard this option as well. Now there's a possibility for option A and option C. Let me go back. Here you can see that this distributed load is applying a downward force. It means that it should be drawn at underside of the beam. And this means that because it's a distributed load, there will be slope in shear force diagram. It means that it should be drawn like this. And this vertical load, it will try to bring the shear force diagram upwards. Now the real question is that will it be like this or will it go straight? So the chances are that it is not going to remain straight. It is going to go down by a certain amount because the reaction over here will be upward reaction, and this force is going to bring it downwards. Now to what extent it will bring it downwards, it will depend on the loading, the point load applied over here. It can be possible that the diagram is like this. It goes up, then it goes down, but it stays over here. If the loading, if the point load is less than distributed load, then we can have this configuration. If point load is more than distributed load, then we will have this configuration, but certainly it is not possible to have this option C. So the correct option is option A. Now this was a quick way of establishing how to draw these diagrams when you have some options available. But how about if you don't have these options, then what do? Then you start from scratch. And now I will show you a detailed way to work out shear force diagram for this kind of beam. So let me open my whiteboard. Here again, these four options are given. So assuming point load is less than UDL. So write it down. Assuming point load to be less than distributed load. So let me draw the sketch. I have a point load of say 50 kilonewton and I have a UDL of say 10 kilonewton per meter, and these distances are same. I'm assuming it's 3 meters and 3 meters. And remember this sign convention for SFD, anti-clockwise forces are positive. Let me draw the shear force diagram over here. The total load due to UDL will be 10 times 6. This will give me total load. Total load due to UDL is 60 and point load is 50, and the sum of vertical loads is 60 take away 50, which means that 10 kilonewtons, because the resultant here is 10 kilonewton. This means that the reaction over here will be upward reaction of 10 kilonewton. So let's draw this diagram first. We will have a sloped line over here from the end till this point, and the value over here is 10 times 3, 10 kilonewton per meter times 3. This gives us 30 kilonewton, and immediately over here we have upward force, and you know that upward force will bring the shear force diagram upwards, and upward forces are drawn on the positive side. Let's bring it upwards. Here it will be 20, this is negative, and at this point again from this 20 I will take away UDL. So UDL is 10 times 3, so 10 times 3, it will leave me 10 kilonewton over here, and finally we have a reaction that will bring this one up to the 0 point. So in this way we are able to draw the shear force diagram. Now how about if the point load was more than the distributed load? For example, if this was 5 kilonewton per meter, then the overall load will be 5 times 6. So total UDL will be 5 times 6, which is 30, and this is downward, and point load is equal to 50 kilonewton, which is upwards. So resultant force will be upward force. In that case we will have reaction at the fixed end as downwards. SFD is going to be like this, but certainly it can't be like option C. So consider both cases. This is negative and this is positive. We already reached correct option. Correct option is option A. Let me now move to the next question. Here we have to identify the correct shear force diagram. Ignoring self-weight, anti-clockwise forces are drawn positive, and this is how it is shown over here. This means that upward forces on right side are positive and downward forces on left side are positive. I would normally start bending moment diagram from right side when anti-clockwise forces are positive. This is generating anti-clockwise moment, and remember that for shear force diagram, positive forces are drawn top of the axis, negative forces are drawn at bottom of the axis. Now this is a very simple example that every civil and structural engineer should know, and I will not be spending too much time explaining this question. We have a load applied here. Load applied is say load of a person, 100 kg person. So 100 kg will be equal to 1 kilonewton. So 1 kilonewton is applied. Imagine this is a wooden plank and there is a river bank on both sides. A person is standing 100 kg, which is 1 kilonewton, and the load is going to be distributed equally over here. this will be 0.5 kilonewton, and again here it will be 0.5 kilonewton. As reactions are upwards, and when I have anti-clockwise shear forces, I will always start from the right side, which means that the diagram here is going upwards and upward forces are positive, so I will draw it in positive direction, and between the end point and the point load there is nothing, so the shear force diagram will go straight, and this is positive side. At this point where point load is applied, I have 1 kilonewton, which means that it will bring the shear force down. This is 0.5 kilonewton. 0.5 take away 1 kilonewton will give me negative 0.5 kilonewton. So this is 0.5 kilonewton but minus, and there is nothing which is applied between this pin support and the point load, so this will go straight until you reach a reaction, and here you will have a negative sign, and at this point you have a reaction 0.5 kilonewton, and that will bring it to the baseline. So this is how we draw the shear force diagram when anti-clockwise forces are positive. If clockwise forces are positive, then simply this part will be reversed, it will be upwards, and this part it will be downwards. But here in this case our sign convention is that anti-clockwise forces are positive. That's why we draw upward forces on the upward side of the axis and downward forces at the bottom side. Let us see what options do we have. Again, it's pretty straightforward that you can't have this option B. This is typical option when you have a uniformly distributed load. A beam with a UDL will have this kind of sloping shear force diagram, and option A is not possible as well because there is a sloping line and it looks like it is a bending moment diagram. It's not a shear force diagram. And how can shear force be zero at supports? It is not possible. When you have supports, you always have maximum shear force at supports, and this is not possible at all. It means that we cross this away as well. Option C, this is the option when you have some kind of a point moment applied at the end when you have a beam. In that case, the shear force diagram, it remains constant. But here it's not the case. We have a point load at the central portion, so that's why we cross this option as well. The only option remaining is option D. So by process of elimination we are able to find this option, and you saw in the example that how did I solve it by having a wooden plank across the river and a person standing in the middle of the wooden plank. It's as simple as that. As engineer, you should be able to at least solve shear force diagram for this question. Now you might be wondering that I'm only solving very simple questions, but it's not the case. Hard questions are yet to come, but I really want to clarify your basics before we move forward. So when I talk about certain aspects of forces, you understand what I'm talking about. We always learn more when we start from simple and progress to very complex structures. So basics should really be priority. Let me now move to next example. Here again we have to identify the correct shear force diagram from the options given to us. Now this problem is little bit trickier as compared to what we did previously. We have to ignore the self-weight, and anti-clockwise shear forces are positive. This is the sign convention for anti-clockwise forces, which means that if we are starting from the right side, upward forces are positive, downward forces are negative. Positive forces are drawn at top of the axis and negative forces are drawn at bottom of the axis. Here we have a pin where a point load is applied and we have uniformly distributed load. Let us see what options do we have and what can we eliminate. So I'll be solving it using two procedures. One is very simple, one by process of elimination. Other is when we have to carry out some kind of detailed analysis. So let us get here. Firstly, it's difficult to say which option is correct except this option D, because we have roller over here and we have pin and loading is applied at pin. So if we isolate pin, the reaction at this point is going to be 0. So in my opinion, option D is not possible, but option B and option A and option C, I don't know which one of them is correct. So let us do very simple calculations to see which option is correct. So we have these options. Let us isolate the left side and right side. We have UDL over here, and UDL is W kilonewton per meter, and here it is L by 2, this is L by 2, and here L by 2 as well, and a load of WL is applied over here. And if I call this as point A and call this as point B and C and D, let's see what reactions we have from here. If you say summation of moment at B is equal to 0, then reaction here VA will be equal to 0. It means that reaction at A, it does not exist. When reaction at A does not exist, it means that this portion of shear force diagram that you see in this option D, it is not possible. So I will immediately discard option D. The next thing, for the second part, if I say here summation of moment at D is equal to 0, then I have this load applied to pin. Load applied to pin is WL plus, this is not half, this is L. Let me rub this off. It is WL times 1.5 L, and this is creating a clockwise moment with respect to D, so that's why it is positive. And then I will have plus VC times L, and this UDL will create some force as well. This will be plus WL, that is total load. So total load will be WL here, times, it is acting at half of the distance from D because it's uniformly distributed load. So L over 2 is equal to 0. This will not be positive. It is creating anti-clockwise moment, so it is negative. So I have 1.5 WL square. I have half WL square, so it will give me WL square. And L will get cancelled in all of them. So it will give me WL. So VC plus WL is equal to 0. And from here, I can say VC is equal to minus WL, which means that the reaction over here is not upwards, it is downwards. So downward reaction of WL. So when you have a downward reaction WL, then we will see how it goes. If this is downwards at point C, then at point D it should be upwards. I can say then that at VD I will have upward force WL. So here I have upward force at point D, that is WL. So now I'm in a position to draw the diagram. At D I have WL, and positive forces are drawn upwards using this sign convention, and I have this W, I have this L. So WL positive, take away WL. So if I take away WL, it will bring it over here. After that, I have a negative WL at joint C, call this as C, then it will go down by WL, and between roller support and here it is WL at pin. Between pin and roller support I don't have anything. This is positive and this is negative. So minus WL plus WL will bring it over here, and between internal pin and outside roller support I have got no reaction. Reaction here was 0. So it means the correct option is option B. option A is wrong, and option C is wrong as well. So you saw that with the help of simple calculations, we can easily solve these structures, and this is what you're going to do in industry. You will be using very simple calculations, and if you can't do it quickly enough, then other engineers will take your job and they will earn all the money. So if you want to earn money in structural engineering, just do these questions quickly. Let's move to the next question now. In this question, we have to identify the correct shear force diagram, and we have to ignore the self-weight as well, and anti-clockwise forces are drawn positive. So this is the sign convention for anti-clockwise forces, and this is how we draw it on shear force diagram. Positive are drawn upward side of the axis and negatives are drawn at downward side of the axis. In very simple terms, we start drawing the diagram from the right side if anti-clockwise shear forces are positive. We will have some options to choose from for this question. As you can see by the looks of it, this structure is indeterminate structure, but we have this internal pin which is making our life easier, and that will make it a determinate structure. Indeterminate structure means that unknown forces are more than equilibrium equations. So here unknown forces are reactions. So there are 4 reactions, but because of this internal pin, one reaction goes away because moment cannot develop at internal pin, and that's the reason this structure would be easier to analyze, because this is a determinate structure now because of introduction of this internal pin. Let us now see what options do we have, and we have these 4 options to choose from. And looking at the options, it's difficult to say which option is correct, and certainly option D may not be right, because the reason is that it is saying we have 0 reaction over here. 0 reaction is not possible. If you have a look over here, we have 2 supports, and at these 2 supports, when loading is applied downwards, these reactions, they have to be upwards. So 0 reaction is not a possibility, so we can discard this option. For others, it's difficult to say which option is correct unless we do some simple calculations. So let us do some simple calculations to find out which option is correct here. Just to simplify the analysis, I'm assuming that W is equal to say 10 kilonewton and L is equal to say 4 meters. And I will separate this beam into 2 parts where we have pin. So one is the right side and other is the left side. So here, separating these 2 parts, there's a pin over here and we have roller over here, a unit load of say, this is 10 kilonewton, this is 2 meters and 2 meters. We have a UDL of 10 kilonewton per meter, and here we have 4 meters. The reaction over here will be equal to half and half. So reaction at this point, I call this as A and call this as B and call this as C. Reaction here at VC is equal to half of 10, which is 5 kilonewton. And we have upward reaction over here on the right side, which is 5 kilonewton as well. And here on the other side of the pin, we will have a downward reaction of 5 kilonewton. When I want to find out reaction over here, it will basically be summation of all the forces on right side. So on right side, I have 10 times 4. So 10 times 4 is 40 plus this 5. So this will give me 45 kilonewton. As this is downward, the total load is downwards. So reaction at A will be upwards. So I can say that VA is equal to 45 kilonewton. And if you want to draw this now, you have all the information here. You have a UDL, you have a point load of 10 kilonewton, and you have a support which is a roller support. So let's draw the diagram, and this distance is 4 meters. This is 10 kilonewton per meter. So firstly, I will have this reaction of 5 kilonewton. I have a reaction of 5 kilonewton here, and I have upward reaction of 45 kilonewton. So firstly, I will move up by 5 kilonewton, and then between this force and the load I don't have anything. Because this loading is coming down, I will come down over here. This is again -5, this is positive, and between internal pin and this point I don't have any loading. This is negative, and at this point I will subtract 10 times 4, which is 45. In that way I will reach over here, and at this point I have a reaction of 45 kilonewton, which will bring this one up over here. So looking at this one, the correct option seems to be option C. The other options are wrong. So our correct answer is option C.